Welcome to The Explainer. Today we're unpacking a genuinely fascinating realm of physics, one that actually led to the 2016 Nobel Prize. We are looking at a completely new class of quantum matter. Picture this, materials that are entirely insulating on the inside, yet highly, almost perfectly conductive on the outside. It's an absolute game changer, a breakthrough that could literally reshape the future of technology as we know it.
Seriously, just imagine a physical substance with this bizarre dual nature premise. At its core, it completely resists the flow of electricity. It acts as a perfect insulator. But right there on its outer boundaries, its edges or surfaces, electricity, and in some cases even light, just flows freely. It sips right around corners and defects with virtually zero energy loss. This is the paradoxical nature of topological materials. And honestly, understanding this behavior is the absolute key to fundamentally revolutionizing modern electronics, computing, and photonics.
To really understand how these materials work, we have to borrow a concept from math, topology. It's a branch of mathematics that explores the nature of shapes, completely independent of deformation. The classic analogy here is a donut deforming into a coffee mug. In topology, because both of those shapes have exactly one hole, the donut's center and the mug's handle, they're actually considered fundamentally the exact same shape. You literally can't lose that hole without breaking the object and changing its fundamental nature. Well, in these physical materials, certain electrical properties are structurally preserved in that exact same way. So, when we apply this mathematical insight to physics, we get what researchers call topologically protected states. This basically means that the electrons zipping along the edges or surfaces of these materials travel in patterns that stay completely unchanged. Even if they hit disturbances, impurities, or defects, they just keep going. Their paths are protected by something called time reversal symmetry. Because of this, electrons travel without scattering and without bleeding off any energy whatsoever, which, let's face it, is a massive leap forward from the highly inefficient conductive materials we're using today. Now, the science here can get pretty dense, so to keep things organized, we're going to categorize and explore this field through 4 distinct branches of topological materials: electronic insulators, photonic insulators, superconductors, and finally, topological semimetals. Okay, let's dive right into our first category. Number 1, electronic insulators, controlling the flow of electrons. First developed back in 2007, these represent a massive leap forward. To see why this matters, let's compare standard transistors to topological ones. In your computer right now, conventional semiconductor transistors require a minimum amount of voltage just to switch between electric states, representing data as ones and zeros. But researchers have envisioned a completely new design. In a topological transistor, the naturally conductive edges of the material serve as the on state. Then, when an electric field is applied, the material is essentially stripped of those conductive edges. It immediately halts the flow and serves as the off state. Pretty clever, right? The stakes for developing this are incredibly high. Right now, global computing consumes roughly 8 to 10% of the world's electricity. And get this, that number is doubling every single decade. If we can build transistors out of topological materials like bismuthene, which is just a single layer of bismuth atoms arranged in a honeycomb lattice, scientists calculate they could consume just half the voltage and 1/4 the energy of standard transistors. We urgently need this technology to keep our electrical grids sustainable in the long run.
All right, moving right along to our second agenda item, number 2, photonic insulators, guiding wavelengths of light.
First developed in 2009, these materials basically force specific wavelengths of light to flow along their exteriors without scattering. They seamlessly bypass corners, imperfections, and even drill defects without losing their signal. Because this light flow is topologically protected, the devices we build from them are incredibly robust, and this brilliantly illustrates how laboratory physics translates into real-world impact. We're looking at highly efficient terahertz frequency lasers that could totally transform cancer screening and airport security. Plus, by using different layered structures to emit mid-infrared wavelengths, we can build vastly superior LiDAR sensors, next-generation pollutant detectors, and even enable free space communication well beyond the capabilities of 5G.
Okay, transitioning now to our third category. Number 3, superconductors, the quantum computing leap.
Topological superconductors are created by pairing a superconducting metal with a semiconductor. The absolute magic of this interaction comes down to an elusive theoretical particle called the Majorana fermion. These are long theorized particles that possess the incredibly strange property of acting as their own antiparticles. Because of this, they are highly sought after to act as quantum bits or qubits. You see, traditional qubits are extremely fragile. They're prone to all sorts of disturbance. But a qubit made from a Majorana fermion, it would be topologically protected. Now, a quick caveat here. It's important to note that conclusive proof of their existence is still being chased by scientists. In fact, a major 2018 study claiming to have found them was actually retracted in 2021. But even so, researchers remain highly optimistic that these will be realized soon.
And finally, we reach our fourth category, number 4, topological semimetals, bridging metals and insulators.
These unique materials sit squarely between metals and insulators in terms of how they conduct heat and electricity. Unlike conventional semimetals, which can easily change states with just a slight tweak in temperature or chemical makeup, topological semimetals stubbornly retain their unique semi-metallic nature despite those environmental changes. Now, what's really interesting is how we can see these complex categories brought to life through specific, cutting-edge laboratory findings. Take a look at some of the data derived from the Shen laboratory at Stanford. Bismuth telluride, for example, functions as a 3D topological insulator with a 100 millielectron-volt bulk gap, making it a prime candidate for room temperature spintronic applications. Then there's sodium bismuthite, which acts as a 3D Dirac semimetal, effectively a three-dimensional counterpart to graphene. And materials like tungsten ditelluride operate as quantum spin Hall insulators, showing very clear, dissipationless edge states.
What makes exploring these materials in the lab so thrilling is how they actually mimic the cosmos. The massless particles, or Dirac fermions, flowing on the surface of these topological insulators travel at about 200 times slower than the speed of light in a vacuum. Because they follow a linear energy-momentum relationship, much like actual light does, these materials give physicists a highly condensed tabletop environment to directly study the physics of relativity. No massive particle accelerator required? But how do we actually see what these electrons are doing? Well, researchers use advanced tools like angle-resolved photo-emission spectroscopy, or ARPES for short. ARPES basically allows scientists to visualize the invisible. It directly maps the electron band structures of the solid materials, which helps confirm complex physical theories, things like spin-momentum locking, where the spin direction of an electron is literally physically locked to its direction of motion. Thanks to tools like ARPS, we are discovering staggering new capabilities. In one massive breakthrough, researchers at Boston College discovered that a topological semimetal called tantalum arsenide can intrinsically generate more than 10 times as much electric current from mid-infrared light as any other material known to science. 10 times! So why does this specific 10x breakthrough matter to you? Because of its extreme sensitivity to mid-infrared light, tantalum arsenide could very soon be used to harvest energy directly from the waste heat of everyday objects. Just imagine capturing the infrared radiation bleeding off heavy machinery, computer servers, or even car engines, and seamlessly converting that lost heat back into perfectly useful, zero-emission electricity. It's truly incredible. What's truly wild about this whole material revolution is that not all of it is strictly new. As MIT theoretical physicist Benjamin Weider perfectly summarized, the next highly desirable solid-state material might be hiding in a 70-year-old paper if you know where to look. And he hit the nail on the head. In fact, scientists recently discovered dramatic topological properties in materials like cobalt monosilicide. That's a material the scientific community has studied and largely misunderstood for nearly 7 decades. So the crucial point we're left with today is this. As we push the boundaries of quantum materials, striving to build zero-loss electronics and error-free quantum computers, the answers might not just be found in synthesizing brand-new elements. The next great technological leap might already be hiding in the forgotten archives of a 70-year-old physics paper, just waiting for us to view it through the lens of topology. Thank you for joining me for this explainer, and as always, keep your curiosity alive.